Hi, I'm Mike Meyer. I'm a principal in the Center for Deep Learning for Electronics Manufacturing, and I'd like to talk to you about deep learning and how we can apply deep learning to electronics manufacturing. To start with, I'd like to set some context around deep learning and how deep learning, artificial intelligence, and machine learning fit together. Artificial intelligence is the broad category that's been around since the 1960s, and it includes both statistical learning and symbolic learning. And we're going to focus on the first category there, the statistical or machine learning. This is a form that's commonly used. Every time you do an Excel spreadsheet and do a curve fit or a linear fit, you're doing a form of machine learning. Other forms include things like decision trees, support vector machines, clustering, and one of the things about these forms of machine learning, in contrast to deep learning, is that you can look at the model and understand what caused the model to give you the answer it did. In a deep neural network or deep learning, that's much more difficult. You have some idea of what's happening in the first few layers, but beyond that, it's very difficult to say exactly why it gave you a particular answer. So let's look at some details of one of these models. Let's look at ImageNet. ImageNet is a classic deep learning benchmark that's been used for many years. There's been a competition for the most accurate recognition of what these pictures are. The ImageNet data set is millions of pictures that have been labeled with what the picture is showing. The idea of the competition is to build a network that recognizes and correctly predicts what the picture is showing. In 2014, for the first time, one of the networks, AlexNet, beat the abilities of humans in terms of the accuracy. And since then, nearly every network is able to match human performance. One of the key pieces to that this shows was that you needed lots of data for it to learn on, millions of pictures, and it turns out you needed GPUs to get the compute capability to apply this. So let's look at some details of AlexNet. AlexNet is a deep convolutional neural network that will recognize images from the ImageNet data set and predict what the image is showing. The first 5 layers are convolutional layers, which will apply the same filter to different sections of the image or the previous layer. Following that, there are a set of fully connected layers which will distill that down to a set of probabilities of the shape of the image being a dog or a cat or a train or a plane or one of 1,000 different types. The way these layers work is that they have parameters that affect how they make that prediction. In this case, AlexNet had 60 million parameters which have to be set during the training process. Each image, to evaluate it, requires over a billion multiply accumulate operations. The training process involves applying this repeatedly to images, looking at the result, analyzing the error in what it's predicting, and then going back and changing those parameters. The training time was previously very long and made it impractical to do this learning in most situations until the application of GPUs. So what we've seen, the reason deep learning has been so popular now is that you can reduce the time by orders of magnitude by applying GPUs to this problem. Although neural networks can beat human performance now, it doesn't mean that they're foolproof. Again, this comes back to the point that neural networks are statistical. It means that they have a high probability of getting the right answer, but we have to be aware that they may not always give the correct answer. In particular, they may be subject to noise, where small changes in the data will cause you to get a different answer, or in cases where it hasn't seen any pattern like the one it's been exposed to, it may make some wild guess. This is part of the reason that it's important to have a rich set of data, but it's also important to understand when you can apply it and making sure that your training set covers those cases. In traditional programming, we write a program that takes some input and generates some output. In the case of deep learning, it's actually a 2-step process, because in the first step, we take our data that we've collected and feed that through the model to assign the values to the weights. This is called training. We take the model with the finalized weights from the training data, and then we use it on our production data that we're seeing live each time and generating the output. So this process means that we have to look at the results both from a training perspective, when we get what we get there, and then what we get when we put it into production. With data, huge amounts of data available on the internet and the GPU compute capabilities, deep learning applications are exploding. Autonomous driving companies and competitors are everywhere, and that seems to be the main thing in the news these days. But there are a lot of places elsewhere in business that deep learning is being applied. It includes things like image enhancement, captioning, fraud detection, surveillance. One that's closer to the problems that we see in electronics manufacturing would be something like medical imaging. And I would like to say that it's not restricted to imaging. There are also applications in automatic speech recognition, natural language processing, recommendation systems. The list goes on. Just so many applications in business are ripe for deep learning. But let's look at a few of them in the electronics manufacturing area. Let's look at some of the challenges that we face in applying deep learning to electronics manufacturing. One of the first problems that we see is that we can be dealing with a lot more data than in other cases. In the ImageNet, for example, all 5,000 categories is about 1.2 terabytes of data in the current data set. In one mask for electronics manufacturing, it is about 540 terabytes of data when we use a 10 nanometer pixel. That's over 400 times larger. In addition, where 3 sigma is considered good for an ImageNet network, we're looking for results in electronics manufacturing of 7 sigma. So we have to recognize and account for those differences in accuracy and the huge amount of data. One area where deep learning can be used in electronics manufacturing is in contour extraction from scanning electron microscope images. In this case, we have an image and we have the reference design data, and we have the simulated results of what we expect the contour to be, and we want to extract that and compare those two. So in this case, the way it's traditionally done is a human will do those measurements. So we're not trying to get 7 sigma, we're trying to get something that is comparable to human performance and yet more automated. So this is a place that we think there is a good opportunity to apply deep learning. Another area where we can apply deep learning in electronics manufacturing is in the area of iterative optimizations. Iterative optimizations take an initial solution, evaluate that, find suggestions on what to improve in that design, and make changes. This can involve hundreds of iterations that take days or even weeks. With deep learning, we can feed results from previous optimizations in and have it learn how to generate a better initial solution so that the number of iterations required is significantly fewer. One such place that we can apply that is in the inverse lithography technology area. And this is a huge opportunity for improving the runtime for ILT. There are many other areas, and we will no doubt explore those as time goes on in electronics manufacturing. But deep learning is going to be something that we need to apply in electronics manufacturing like people are in all other industries. And we look forward to the challenges here. Thank you.